Hello, all you network administrators out there looking to learn how to do something quickly. Welcome to part 2 of deploying Layer 2 NAT with Cisco's Industrial Ethernet Switching. My name is Albert Mitchell, and if you have not seen part 1, it's advised that you do so. We're going to quickly recap part 1, just in case you haven't gone back to watch it. It's only 15 minutes or so. Then we're going to start talking about different ways to use L2NAT to solve the same problem and the pros and cons of different ways of doing it. And then we're going to sort of wrap it up. So getting back to what is Layer 2 NAT? It is a one-for-one IP address translation, meaning there's one inside and one unique outside IP address. Does not do 1 for N. It's not NAT-PAT. Doesn't do layer 4 port address translation. Does work at line rate because it's industrial Ethernet switch. It's not CPU bound. Bidirectionally. And we're going to use the terms inside and outside and public and private a lot, sometimes together, sometimes separately. But you need to know that the inside is the duplicated IP addresses and the outside is where things are unique and routable. So the switches can work with ICMP and ARP, and we call those out specifically because those are two of the known IP protocols that put IP addresses into the payload. And say when we say fix up those protocols, we also mean we're going to translate the IP address in the payload as well as in the layer 3 header. And I use this example throughout the document or throughout the presentation, but it can be any IP address. And if you saw video 1, you'll notice or you'll recognize my sophisticated machine. And what we're really trying to say here is sophisticated machines have internal networks that they use static IP addressing to identify the components in the machine. They come with a dual NIC, typically a controller, which has a network administration assigned IP address on the outside. In this case, it's 10.0.0.100, and would have an internal IP address as well to communicate with the other components within the machine. And if the only component within the machine you have to communicate with is the controller, then you don't really have a problem that Layer 2 NAT needs to solve. It's when you need to communicate with devices or components inside the machine that you have a problem. And you're going to notice in this example is we pick on the HMI. So the HMI is a component inside the machine that you need to communicate with. And the problem is you've got multiple machines that all have the same HMI IP address. So in video 1 or part 1 of the video, we talked about how you could solve that problem. But what we've really done is sort of created another problem, unless you're careful about how you do it. So what we're saying is here is that because we used a permit all in part 1 video when we showed our solution, permit all is really permitting everything. And so the broadcasts are going out from machine 1 to machine 2 to machine 3 and vice versa. So all the machines are seeing each other's broadcasts. And the problem really is the ARP. So when some component, let's say for instance the internal controller of machine 1 wants to ARP for 1.5 to get the MAC address, that ARP is seen everywhere. And so you're going to get an ARP reply from every machine on the broadcast domain that has a 1.5. And once this happens, generally machines come to a stop because they don't know who to communicate with, or they're trying to communicate with a device that's not in their machine, and pretty much everything just comes to a grinding halt. So if you make this mistake, you'll notice real fast. So there's a couple of different solutions that we're going to talk about here. And the one that I use the most often is called routed access. And really, this works by using an internal VLAN and an external VLAN, and then subnets or IP addressing to route between the two only for those components inside the machine for which you need to communicate outside. In this particular case, we can still use the permit all if you look at bullet 2, because the internal and external VLANs are not the same. Therefore, the broadcasts within the machine for ARP, for instance, are not escaping the machine itself, because it's a layer 2 broadcast, and VLAN 3004 is not a member of the uplink out of the machine. So the link between the IE switch and the zone switch does not contain VLAN 3004, so those broadcasts do not escape. The other solution, or solution 2, is to not use permit all. And in this case, we are going to keep the same VLAN on the internal and external, and the IE switch is not routing in this case. The IE switch is continuing to do layer 2 forwarding. By not using permit all, the broadcast or the NAT requests for those devices which do not have a rule are simply dropped because there's no rule matching it, and they are discarded on the interface for which the layer 2 NAT instance has been applied. And we're going to go into that in a little more detail. So if that's not clear right away, it's okay. We're going to get to it again. So this is more of a for reference, but within scenario 1 with routed access, there's 2 different ways to do it. And really the difference is whether you want to have 2 IP addresses on the IE switch, where, like in the example, VLAN 200 had a layer 3 interface on that VLAN, and VLAN 3004 had a layer 3 interface. So you have 2 IP addresses on the 2 different VLANs representing the 2 different subnets, and you're routing that way. The other way is saves on IP addresses to some degree, but you have a single IP address, and this is routed scenario 1B. You have a single IP address for the IE, which is internal. And then to communicate with the IE switch, you have to translate its IP address. So that the switch's own IP address is layer 2 NAT translated. And then scenario 2 is one we talked about with a single VLAN, where the data and the management are sharing the VLAN, and the permit unmatched is not recommended. So do not permit unmatched. So the only one where you can permit unmatched is scenario 1A. And while scenario 1A using routed access may seem more complex, or may even look like from the outside as if you're doing more of a router or firewall type of layer 3 NAT, because we are routing it. So it may look or appear that way, although that's not what's happening. It does permit for unmatched. And the beauty of that is you don't have to worry about whether you're going to accidentally deny some communication, which is critical. So it does provide some flexibility in that the network administrator, you don't have to worry about whether the unmatched traffic is going to be dropped or not. So let's just jump into solution 1, which is outside and inside are using different VLANs as part of a routed access. Just to reiterate, the idea is this eliminates the broadcast across machines because we're using different VLANs. Every machine would still use the same internal VLAN and the same subnet, so that doesn't really change. And the advantages are, a single VLAN from which you have to manage the switch. There's no concerns with the permit all about blocking traffic, but the disadvantage is you are now deploying routing in the access layer. At least you're deploying routing in the access layer for those devices which you want to translate, and this can be considered more complex if you're uncomfortable with routing in the access. And so if we go back to our sophisticated machine, it would look something like this. Now what we've done is we've put the layer 3 gateway for the internal machine on VLAN 3004 is now on the IE switch itself. So in part 1 video, we showed the zone switch as being the gateway for 3004, and it had 192.168.1.1 IP address associated with the zone switch. Now in this solution, the gateway for the internal machine is now the IE switch itself. So it is the gateway for all the devices, and specifically for our HMI device, which needs to communicate outside the machine, it's going to use that gateway, and we're going to show that here in a second. And then one of the differences between solution 1A and 1B is the IP address on VLAN 200, which we're going to see in the next slide. So here's our sophisticated machine and our L2NAT instance definition. Looks like this. So if you note the highlighted one, we now only have a single rule, a single host rule in our layer 2 NAT instance, and that is for the HMI itself. And you'll notice now we have an IP address on VLAN 200, which is in the public space, and it is unique. And we have an IP address on VLAN 3004, which is 1.1, and that is the gateway for the machine itself. And you would consistently put this IP address on every machine instance. So machine 2, machine 3 would all have an interface VLAN 3004 with the 1.1 IP address. And again, the permit all is safe in this particular case. In solution 1B, the difference from it in 1A again is the single IP address on the IE switch on the data VLAN, which is VLAN 3004. Let me build out the NAT definition here in the configuration. So you'll notice now, because we have a single IP address, that the host rule inside the NAT instance has two rules, and one rule is to translate the switch's IP address itself. And we can put the switch into access mode on the interface. So now we don't actually have to have a trunk. We have a single VLAN coming in, and the switch uplink is in access mode on VLAN 200. And even though we don't have an IP address on that, but that's okay because the upstream switch only knows about IP addresses on 10.0.0x subnet anyway. But the problem with this is you can't use permit all. It's not safe. So this is really in theory only. I show this because this is how you could do it, but it's not really what I would prefer. And if you were to call me in as a consultant on this, this is not what I would recommend. And also in doing something like this, what I'm not showing is you would almost certainly have to define a route on how to route 192.168.1.1 into the rest of the network, and that's not really shown, but you would definitely have to do that. So let's go back to 1A again and show you how this might work. This is, if you saw the part 1 video, this looks familiar. We have our data collection app, we have our zone switch, we have our HMI on the right with its gateway as 192.168.1.1. And now because we're doing 1A, that is on the IE switch itself. As you can see, we only have the single rule inside the NAT instance shown highlighted there in yellow. We are back in trunk mode, and so we are going to apply this to VLAN 200. So when you look underneath the definition for gig 1.1, you'll notice that the layer 2 NAT HMI machine 1 is saying 200, that is VLAN 200. It's because this, in this case, with this definition, VLAN 200 is tagged. And taking note here, as I've been showing consistently, but this differs from the video in part 1, is these are different VLANs. And now we are going to route from VLAN 3004 to VLAN 200, or route between those subnets rather. And if you had something like this set up, this is what your ARP table may look like. Note that you are learning IP addresses on both VLANs, both internal and external. Anyway, this is a quick example showing the switch's own ARP table. So now let's do a little packet walk on what this might look like. Again, we're going to use the same example from the part 1 video where the data collection app reaches out to the HMI machine. The HMI machine is going to ARP and then finally respond to the data collection app. So it will ping the HMI machine using its public IP address of 10.0.0.99, shown there in yellow. It comes into the zone switch. The zone switch routes it, so it changes the MAC addresses. It now comes into the layer 2 NAT switch, but now because it's been routed, now the destination and source MAC are changed, because that's what happens when you route, and also the destination IP address has been translated to 1.3. Note that the source IP address was not translated. There's no rule for it, so it goes through unchanged. Now, the HMI is going to ARP for its gateway, and this time it doesn't leave the IE switch, because the IE switch is the gateway. So it quickly responds back with its own MAC address as the MAC address to use for 1.1. And now the HMI can respond to the ping. It sends the request to the IE switch, which is its gateway, with its own source IP address. The IE switch will now route it, and you can see that the source and destination MAC addresses have changed to EE and CC respectively. The source IP address has been translated to the HMI machine's 10.0.0.99, and the destination IP address has not. And then, of course, the zone switch will route this to the data collection app. So this is how it would work differently if you're using the layer 3. The ARP itself doesn't leave the switch, but the fix-up was still there. In this case, we used ping or IC, and so the fix-up was there. From a translation perspective, not much has changed, and the only change is now we're using multiple VLANs and routing. So if we were to take a look at this at the zone level, showing multiple machines, we would see that every switch, every machine rather, is now having a unique IP address on VLAN 200, and only VLAN 200 is leaving the machine. So we have a broadcast domain on VLAN 200 for all the different machines, but that's okay. It only goes to the IE switch itself and then stops, as well as includes the controller for each machine. So one thing you could do if you were to do something like this, and I say, hey, I've got 2 cables coming out of my machine, I don't need to do that. So I could remove the cable from the controller and instead connect the cable to the IE switch. And now, of course, the difference being that the interface between the controller and the switch for the 10.0.0.100 is VLAN 200. So you have to make sure that your VLAN, that the interface connected on the machine is set to be a VLAN 200 interface and not a VLAN 3004 interface. But you savvy network administrators already know that. Let's take a look at solution 2, where we're going to use the same VLAN for inside and outside, but not use permit all. So we're going to do, I'm calling this layer 2 forwarding in the access layer to differentiate it from a routed access in the access layer. So we have a single machine with working on VLAN 3004, the same VLAN inside and outside. The big difference when you see the configuration is you cannot have a permit all in your layer 2 NAT instance definition. This will block the broadcast that we saw earlier. And we're not really going to show much about the routing anymore, and so the switch's IP address is not that relevant because it's no longer involved in any of the forwarding. So it's all layer 2. So let's take a look at our instance definition. Looking at the layer 2 NAT instance definition, we see that now we have a inside and outside for the gateway, which we have to go back to doing now. We're now making layer 2 forwarding decisions, and the gateway is the zone switch. And we are going to put the layer 2 NAT definition on gigabit 1/1, and on 3004 it's a tag VLAN. We have to apply the layer 2 NAT instance to 3004. The big difference here is that there's no permit all in the layer 2 NAT instance definition. Only packets with an IP address translation rule are forwarded, or rather permitted to go through the interface, only for VLAN 3004. Right? So packets on VLAN 200, because we did not apply a layer 2 NAT instance to VLAN 200, are not impacted. There's no deny on VLAN 200 like there is for VLAN 3004. And if we take a look at this across the machines, so if we did something like this across the machines, they're all on the same VLAN again. Yes, we do have the big broadcast domain, but you'll notice in yellow at the definitions down below is the host, the HMI machine in this case, has a unique IP address on each. And if you plan to deploy this scenario, I suggest you test it first. While you all definitely block the broadcasts from components inside the machine that do not have a rule, what you may need to test for is for any of your HMI equivalent components, so any component inside the machine for which you need to translate, does it ARP? Because there's a rule for the HMI machine, or the your component for which you need public communication. If it issues an ARP for other components inside the machine, then you may need to use solution 1A. But again, you need to know your internal software of your machine if this is happening or not. If this is happening, you can either go to solution 1A, or making this slightly more complex is now you could put a potential security ACL either on the zone switch or on the uplink interface on the IE L2NAT switch to do a deny on any packets coming in, which would be like an ARP response from a component in another machine. So things start to get a little more complex if you want to go with this solution and your component for which you're trying to translate to the outside issues ARP, which could escape. Just be aware of that. And that's why I suggest that you test. So now what about rings? Rings are a very popular thing in industrial networks. We do rings for cable saving most of the time. So rather than home run cables from various parts of the manufacturing or your industrialized deployment, you just connect it to the adjacent IE switch. And so we often see rings. So the question is, can you do it in a ring? And the answer is yes. This is showing how you could do it across, with a ring of 5 here, in which you're going to do layer 2 NAT on 4 of them. The trick here is you actually have to have a rule for every host, and you have to have permit all. And of course, you need, every rule has to have the public IP address has to be unique, and you can sort of see some examples of it there. And you apply the NAT instance on both interfaces, because in rings, you don't know from which direction the packets will ingress from. So they could ingress, from either interface, gig 1 or gig 2, and you have to have a translation for it. And what happens here is if the packet doesn't match because the packets on the ring, for the most part, are all public, right? So they're all public IP addresses on the ring, and you have to keep it that way. And if the public IP address on the ring doesn't match the rule, it just gets forwarded through, right? And no translation is done. A few more details on this. Again, all the end devices have a translation that are going to be on the ring itself. Again, no untranslated IP addresses, because likely those are duplicated if you have a component on there that you don't want translated. But again, we're talking about these machines, and if they have a component that exists in every single machine and it is ARPing or doing something onto the ring and there's no rule for it, now all of a sudden you've got a 192.168.1.x ARPing on your ring, and you'll get lots of responses, which will probably bring the machines to a halt. So what about if you want to do something for multiple devices and you don't want to use lots of host rules? So one of the things that we have is something we call a network rule. So you can do this instead of just translating end devices with the host rule. And what you end up doing is something very similar when you build any kind of ACL or anything like that. You end up using a mask. And so in this case, we're showing an example there on the bottom left where we are going to translate with a mask a /28. A /28 is the smallest mask that you can use. And essentially, it will work for 16 hosts, which is the smallest network rule that you can use is 16 hosts. And so if you're going to use this in this particular machine, you would essentially be wasting, 12 IP addresses, because you're going to have only showing 4 potential components inside the machine. You'd be wasting 12 IP addresses. So probably in this case, you wouldn't use a network rule, but we're going to, it's just here just for showing you how to use it. And so what you can see on the right is what this means is wherever the bits in the IP address are not masked, they are unchanged. So the simple example on the right where you show 192.168.1.5 is translated into 10.10.0.5. Yeah, that makes sense, right? Because we're just not translating the last byte. But in fact, what we're really not doing is we're not translating the last nibble. So pay attention when we look at the other machines. So we have to assign unique IP addresses or networks to machines 2 and machines 3. So you'll notice now that in yellow, we've had to add 16 to the outside public IP address to make it unique. And so whereas machine 1 was 10.10.0.0, machine 2 is 10.10.0.16 because we're using a /28 mask. And the same thing with machine 3, it has to start at 32. And now if you look over on the right with the little blue arrow, you'll see that the component in machine 2 with 192.168.1.5, that gets translated to 10.10.0.21. So only the last nibble is not translated, and the 16 is part of the resultant public IP address. And so machine 3, instead of having .21, would have had .37. Let's just take a minute and just dive into this a little bit more, just so you fully understand. Again, we're talking about the unmasked bits. And if we take a look at the row at the bottom, now we have rule 1, we have a /24. And now we're talking about the entire last byte of the IP address is not translated. So you take a look in the column on the right, you'll see a couple of examples. And in this case, because we have a /24, both IP addresses are translated. Now we go back to rule 2, row 2 now, and we're using a /28, and we take a look at our IP addresses. And you'll notice that only 192.168.1.3 is translated. 192.168.1.129 is not translated. Why? Because it didn't match the mask. There's and row 3 shows the same thing, but just like the example we showed before, now we have a .128 as part of our translated public IP address, and so now the 1.3 in the original IP address becomes 131 because we had to add 3 to the translated IP address. Right? And then finally, when you look at row 4, we have a /16 mask, and essentially what this means is the .128 you see there in yellow is ignored because it's outside of the mask. And you can see there the resultant IP addresses on the right-hand side. So we're not going to spend too much time here in troubleshooting. I will say that I found the use of show layer 2 NAT statistics CLI command to be invaluable when trying to troubleshoot something like this. This example here is a truncated output. I didn't show everything here, but I did want to focus on the fact that it does show ingress and egress, as well as ARP and ICMP, packets translated, packets not translated, packets bypassed, and you can clear this. So if you have to make a change to your configuration and try again, you can clear the layer 2 NAT statistics. So this is pretty useful in figuring out if your rules in your layer 2 NAT instance definition are working. So let's wrap this up. They duplicate the IP addresses on purpose. It just makes the machine software development easier. And the Cisco IE switch solution is 1 for 1, 1 inside for 1 unique outside. Single box solution, we talked about this in the part 1 video, where other alternate solutions are to use a layer 3 device such as a router or a firewall. That just adds a lot of complexity and one more device to manage. Be careful with your permit all. So if you wanted to get more information outside of just this video, if that was needed, we do have a layer 2 NAT configuration guide. We're showing it here. Well, this is going to come up for the IE 2000 or the IE 4000, but the layer 2 NAT behavior is consistent across the industrial Ethernet switching products. So one configuration guide will document how it works for all the IE switches that support layer 2 NAT. If you want to see layer 2 NAT inside of a solution, the CPWE stands for Connected Plant-Wide Ethernet. This is a solution document that has a specific chapter on layer 2 NAT as part of a solution. And also, a shameless plug, the IoT networking team within Cisco has our own YouTube channel where you can find more information about layer 2 NAT, where you would also find the part 1 video, as well as lots of other interesting stuff on features and solutions we have within Cisco's IoT networking group. Hey, thanks for watching all the way to the end. You rock.